Alright, I'm in the Pilot's Handbook of Aeronautical Knowledge, Chapter 4, page 6, 4-6, Lift-to-Drag Ratio. Drag is the price paid to obtain lift. The lift-to-drag ratio, the L/D, is the amount of lift generated by a wing or airfoil compared to its drag. A ratio of lift-to-drag indicates airfoil efficiency. Aircraft with higher lift-to-drag ratios are more efficient than those with lower lift-to-drag ratios. In unaccelerated flight, with the lift and drag data steady, the proportions of the CL and coefficient of drag, CD, can be calculated for specific angle of attack. CL. The lift-to-drag ratio is determined by dividing the C by the CD, the CL lift and the C drag, which is the same as dividing the lift equation by the drag equation. All terms except coefficients cancel out. L equals lift in pounds, D equals drag. Where L is the lift in pounds, CL is the lift coefficient. And that little P thing is density pressed in slugs per cubic feet. And V is the velocity in feet per second. And Q is the dynamic pressure per square feet. And S is the wing area in square feet. So, C over D, coefficient of D, equals the ratio of drag pressure to dynamic pressure. Typically, at low angles of attack, the drag coefficient is low, and small changes in angle of attack create only slight changes in the drag coefficient. At high angles of attack, small changes in the angle of attack cause significant changes in drag. So, lift equals the coefficient of lift times the density times the velocity squared times the size or square feet of the wing, and the drag will equal the coefficient of drag times the density times the velocity squared times the size of the wing, square foot of the wing, and divide that by 2. So the first one, the lift one, you would divide by 2, and the density one divide by 2. The above formulas represent the coefficient of lift, CL, and the coefficient of drag, CD, respectively. The shape of an airfoil and other life-producing devices, i.e. flaps, affects the production of lift and alter with changes in the angle of attack. The lift-to-drag ratio is used to express the relation between lift and drag and is determined by dividing the lift coefficients by the drag coefficient, coefficient L, divided by coefficient, or it's just coefficient L / coefficient D for drag. Notice in figure 4.9 that the lift curve, red, reaches its maximum for this particular wing section at 20 degrees angle of attack. And rapidly decreases. 15 degrees angle of attack is therefore the stalling angle. The drag curve yellow increases very rapidly from 14 degrees angle of attack and completely overcomes the lift curve. Drag curve yellow increases very rapidly from 14 degrees angle of attack and completely overcomes the lift curve at 21 degrees angle of attack. The lift-to-drag ratio in green reaches its maximum at 6 degrees angle of attack, meaning that at this angle the most lift is obtained for the least amount of drag. Note that the maximum lift-to-drag ratio, lift-to-drag max, occurs at one specific coefficient of lift and angle of attack. If the aircraft is operated in steady flight at the lift and drag max, the lift-to-drag ratio, the total drag is at minimum. Any angle of attack lower or higher than the lift-to-drag max reduces the lift-to-drag and consequently increases the total drag for a given aircraft's lift. Figure 4.8 depicts the lift-to-drag max. By the lowest portion of the ordered line labeled total drag, The configuration of an aircraft has a great effect on the lift-to-drag. We'll hold off there. That was a lift-to-drag ratio. See ya.